Let us continue to our topic. So this is the arrangement of the clutch and turning gear. So this is your flywheel, engine flywheel. This is your forward clutch. This is your flexible tire plan. And this is a reverse clutch. So propeller plans and main gear. So this gear is not properly draw. Let us skip to this. This is arrangement of the clutch and gear. So we have here forward driven gear, input shaft, reverse driven gear, output gear wheel, this one output shaft, clutch plate, this one is hub, this one is pressure plate, and forward clutch spider, and forward pinion. So here, this one is output shaft, output gear wheel, input shaft, reverse driven gear wheel, reverse pinion, reverse clutch spider. So this is the arrangement of the transmission of the car. So as you notice here, this one is engine, this one is pressure plate, this one is pressure plate, and this one is this I forgot already. As you can notice here, this always engaged, but there is no load if the clutch is not engaged. You see, this one, if this one engaged here, this one is turning. So you see, now it's not in neutral, it's not turning. Now if this one is engaged, you see it's turning, this one spitting, so that the propeller shaft will turn and your wheel on your car will turn, so the car will move forward. So this is the arrangement of the transmission. So the same also with the gearbox. Describes how a diesel engine is prepared by for standby. Always use pre-departure checklist and preparing your engine raw machinery for standby and ready for departure. So this is your machinery. This is the overview of your machinery. This is main engine. Now auxiliary engine DG1 and 2 already parallel. Your supply of fuel is running, your cooling, everything is running. See, if green is running, so you need a checklist to prepare this machinery for departure. Describes the method of starting and stopping reverse and reversing of a direct propulsion diesel engine. How do ship engines start? Diesel engines on ships are started by supplying compressed air to the engine cylinders in the appropriate sequence for the required direction. Cylinder air start valves are then open, enabling the compressed air direct from the receiver into the cylinder. Now, most common forms of methods used on board ships are manual, electrical, and mechanical systems. So these are the common starting system on board. So this is one example of air starting system. Now when you push this lever, you open the air to your pilot valve, to your pilot air. So the air is coming from your air tank. If you open this valve, it's going there, the air going to the pressure regulator and going to the your control lever. So if this one, you push this one will open. So there is air here. pilot air and opening this valve here, so that the 30 bar pressure air pressure will go here to your starting valve here in the inlet. So when this cam is turning, you see this distributor is opening and giving pressure here to the starting valve to open the starting valve. When this starting valve piston is pushed, the starting valve is spinning, so the air pressure going to the air cylinder, the engine cylinder, pushing the piston downward, so that the engine crankshaft will turn and the engine will be running. So this is the example of the reversing system. See, if you reverse the engine, this one will turn the cam here. If you start the engine forward, the cam is here, so giving the this one is the reversing. You see, you put air here to move the piston, so that this one will the lifter will transfer to other side of the cam nose, and if this one will release the air pressure here is released, so this one is transferring here this lifter, so that the engine will turn reverse. States that the number of starts is limited by the capacity of the starting air reservoir. 12 starts, a supply of compressed air is stored in air reservoirs or bottles ready for immediate use. Up to 12 starts are possible with the stored quantity of compressed air. The starting air usually has interlocks to prevent starting if everything is not in order. So for example, this is your main engine. You start this one, so you can start 12 times with the capacity of the main air tank. Describes the waste heat recovery system of two-stroke main propulsion engine. The waste heat recovery system recover the thermal energy from the exhaust gas and convert it to electrical signal, while the residual heat can further be used for ship services such as hot water and steam. So we have here your main engine. So the exhaust of your main engine will pass through economizer here. See here. So in the economizer there is circulated boiler water here. So this boiler water will be heated by means of your exhaust gas, the temperature of your exhaust gas. So this is waste energy recovery. So the heat of your exhaust gas will heat the boiler water to produce steam. So your exhaust gas will proceed to, or will flow to exhaust pipe to atmosphere. So that is the waste recovery. So there is a damper here. So if the temperature of your boiler water is reached into normal temperature, the damper here will open and the damper here will close, so the exhaust gas will flow here to the exhaust pipe going to atmosphere. So that is the waste recovery, energy recovery. So here you see you have exhaust gas, so flowing here, and there is a flow of boiler water here. Your boiler water is boiling and generating steam. You see here the boiler water is in low temperature when already heated here, it's become high temperature and producing steam. So this is boiler recovery, the energy exhaust gas uh, heat recovery system. So waste heat. Describes the turbine, the feed system, and the boiler system as a system. The feed system is made up of four basic items: the boiler, the turbine, the condenser, and the feed pump. The boiler produces steam which is supplied to the turbine and finally exhausted as low energy steam to condenser. Say this is your uh, turbine. This is your turbine. So here you have the boiler and producing steam here, and this steam is used to turn the turbine, and the turbine is coupled to your alternator and you are producing electricity. So the steam here is being used, the turbine will flow to will exhaust to main condenser, and there is a you see seawater here. So there is a heat rejection here, and this uh, steam will convert it again into fresh water. So it will sucked by the feed pump and uh, deliver again to your boiler. It becomes non-boiler water. So this is the cycle of the basic steam cycle. So you have here your boiler. So you have here the feed water inlet. It will flow to the through your down camera. So this is your water drum, boiler drum, and this is the riser. This is down camera. This is the riser. So the hot water will go up there and now producing steam. So you have here the fire, the combustion chamber to heat this water to generate steam. So this is the basic steam cycle. First, your feed water is located in here in the hot well or casket tank. It will be sucked by the feed pump and it will deliver to the boiler, and there is heat supplied here from your burner. Then this one will boil and generate steam. The steam will flow there to your turbine. The turbine will run, and this turbine is connected to a generator, so it will create electricity. So after the steam is used in the turbine, it will flow to your condenser. Then there is a heat rejected here. Yeah. So your steam temperature will be absorbed here by the cooling water, and this steam will become condensate again, and it will take suction your extraction pump and deliver to the hot well, and this is the basic steam cycle. Explain the working principle of impulse turbine and reaction turbine. The impulse turbine, first, all pressure energy of water convert into the kinetic energy through a nozzle and generate high-speed jet water. This water jet strikes the blade of turbine and rotates it. In the reaction turbine, there is a pressure change of water when it passes through the rotor turbine. So this is your impulse and reaction turbine, the working principle. You have here the steam or water nozzle, both side here, and this steam pressure pushing force to the blade, and your turbine will turn. So when water or steam come from the nozzles, then it will push the nozzle in backward direction and turbine will start rotating. Stop my recording here.
The function of a closed-loop system is to monitor and automatically maintain a variable at a desired set point in a manufacturing process. Using an example of a heat exchanger, the operation of a closed-loop system is compared with a block diagram. The heat exchanger supplies heated water to a food processing operation. Cold water enters the bottom of the vessel where the water temperature rises as it passes through steam-heated coils before flowing out of the pump at the top. Each block represents a function of the operation. Lines connecting the blocks indicate input and output signals of each function, with directional arrows indicating the process flow. The controlled variable is the actual variable maintained in the process. In this example, the controlled variable is the temperature of the water leaving the tank. Measured variable monitors the status of the controlled variable. Water temperature is the measured variable in the process. The measurement device senses the measured variable and produces an output signal that represents the status of the controlled variable. The thermal sensor that measures the water temperature in the heat exchanger is the measurement device. The sensor provides an electrical signal to the controller and is defined as the feedback signal in the block diagram. Set point is the predetermined value of the desired condition of the control variable. In the heat exchanger, the set point is the programmed value of the water temperature leaving the tank. Error detector compares the set point to the feedback signal and produces an output proportional to the difference between them. Error signal is the output of the error detector. If the feedback signal and set point are equal, the error signal is 0. The controller is the brain of the system. It receives an error signal as it inputs and provides an output signal to the final control element or actuator in this example. A signal from the controller causes the controlled variable to match the set point using the actuator of the system. The flow valve represents the actuator, where steam flow is controlled. The amount of energy or steam in this example, altered by the actuator, is the manipulated variable. Manufacturing process is the operation of the heat exchanger to control the physical variable. Disturbance is defined as a change in the manufacturing process resulting in a change in the control variable. Disturbances occur when the water temperature suddenly changes or stops flowing. Closed-loop control and the associated terminology are common within manufacturing systems where precise control is required.
Hey, hello guys, this is Chinmaya, and in this video we are going to look at open loop and closed loop systems. Let's begin with open loop systems. Consider a system. Now this system is going to have an input signal which can be, say, an electric one. Now the output here that you get is obviously dependent on the input signal. However, you don't have a feedback signal that tells you how to vary your input, when to increase or decrease the input to get the desired output. A classic example of an open-loop system is your immersion heater. The immersion rod that you put in water to heat it. Yes, that one. It goes on heating the water, but it doesn't really have a feedback mechanism to tell you how hot the water is and when to stop heating the water. Now let us look at closed loop systems. As you must have already realized, the differentiating factor for a closed loop system is the presence of feedback. Consider a system. Let's give it a nice input signal. And we have an output. However, we also take feedback from the output signal, where the margin of error from the desired output is determined. This is now fed into a controller which varies the magnitude of the input signal so that the desired output is obtained. Well, to sum it all up, we take the feedback signal from the output and feed it to an error detection circuit, which tells the magnitude of error to the controller, which then determines the magnitude of input that is supposed to be given to the system. This will lead to getting the desired amount of output. A good example of a closed loop system is our air conditioner. It constantly takes feedback from the room temperature and thus causes the compressor to shut down and start over again, and thus maintaining the desired room temperature. An example on similar lines is that of a water heater, which allows you to set the temperature of the water. So in this way, it constantly keeps measuring the temperature of water inside and thus turns on and off to maintain the temperature of water. Now that we understand what open loop and closed loop systems are, let us put down what we can call the pros and cons of these systems. The accuracy of the output in an open looped system is low because of the absence of feedback. An open looped system is of course easy to construct because there is no feedback circuitry involved. And with all this, an open looped system is less expensive to construct. A closed loop system is of course more accurate and more reliable because of the feedback circuit. Of course, these are complex. And also, they are expensive compared to an open loop system. These are what I call the characteristics or probably even pros and cons of these circuits. And finally, what makes them both different? The presence of feedback. Hope you found the video informative, guys. Hey, hello guys, this is Chinmaya, and in this video we are going to look at open loop and closed loop systems. Let's begin with open loop systems. Consider a system. Now this system is going to have an input signal which can be
The function of a closed-loop system is to monitor and automatically maintain a variable at a desired set point in a manufacturing process. Using an example of a heat exchanger, the operation of a closed-loop system is compared with